Alright, so in this lesson, what we're looking at is finding equations of tangents and normals like we did in the last one. In the last lesson we used parametric equations, and we found the derivative using the chain rule from the parametric equations. You remember in the last lesson I put up two headings. One was using parametric equations, one was using implicit differentiation. Okay, so that's where this lesson fits in with the last one. This is the implicit differentiation method. So to contextualize why we need some other differentiation method, let me give you an example. Find the equation of the tangent, and we'll just stick with tangent at this point rather than the normal as well. Find the equation of the tangent to the curve x squared plus y squared equals 25 at the point 3, 4. We know that to find the equation of a tangent, we use y minus y1 equals mx minus xy. Well, this question's really convenient because it's given us an x coordinate and a y coordinate. So we already know x1 and y1. The only thing we're left to find is m, the gradient. Now the problem with this equation here is that to find the derivative, normally to find the gradient we need dy dx. This is dy dx, the gradient at a particular point. But in order to get dy dx, what do we really need? What do we really need in order to find dy dx? What would be the equation that we need before that? Maybe a vague question. We need an equation of y equals. And the problem here is that we don't have an equation with y equals. Yes, we could rearrange it. We could rearrange this. But to get y equals, we're going to need to take a square root, which will actually give us the plus or minus. And so we'll actually end up with y equals two separate functions, one the positive and one the negative. And just to contextualize that, remember this here is the equation of a circle with a radius 5. And so if you go way back to your Maths B work, you remember that is a circle defined as a function. Remember the rules for a function? For every x value, there can be at most one y value. But this one, for this particular x value, there's two different y values. So this is not a function. It's not a function. And that's why we can't differentiate it from this point using our normal methods. This is actually, the circle is actually made up of two functions. That and that. The top half and the bottom half are each individual functions. So, while this is given as an equation, it implies that there's other functions, there's other inbuilt functions within this equation. So rather than having to rearrange to get y equals and then differentiate, we can use a method called implicit differentiation to get us the dy dx value. So how do we do it? Okay, to find dy dx. Take the equation and differentiate every term with respect to x. For example, or therefore, x squared plus y squared equals 25, and I'm going to differentiate each term with respect to x. Alright? The derivative of that with respect to x, the derivative of that with respect to x, and the derivative of 25 with respect to x. It's an equation. What I do to one side, I do to the other. Okay? What I do to one term, I do to all the terms. It's still correct. Now, before we go on, I'm going to rub out what I write here in a moment, but let's go back to some really, really simple differentiation. Go back to some simple stuff. If you had y equals x squared plus 3, if we were to differentiate, we would differentiate that as dy dx. Which we could write as the derivative of, not y, well y is actually x squared plus 3. So our notation here, where we've just normally just written dy dx, it's because y is explicitly opposite of this. Y is explicitly a function of x. Okay? So dy dx is really the derivative of x squared plus 3 with respect to x, which we know the answer would just be 2x. Keep that in mind. I did that to link this notation here because you probably haven't seen it written like this too much before. So the derivative of x squared with respect to x is just really like what we did here. So I rub that out. What is the derivative of x squared with respect to x? 2x. Yeah, 2x. But the problem is here, I'm now, on this term, I'm now trying to differentiate y squared with respect to x. That would be okay if I had y squared equals something with x in it. But let me show you what we can do here. I'm going to modify this, and I'm going to say, well, I could actually differentiate y squared with respect to y. I can do that. And then if I multiply that by dy dx, does this expression, this is a bit like the chain rule expression, does this expression here, is it equivalent to that? What could happen with your dy's? Effectively, they don't really, but effectively. And that would leave you the derivative of y squared with respect to x, which we've got there. Now, you'll see why I've done that in a minute. Equals derivative of 25. What's the derivative of a constant? 0. Okay, so just finishing off here, 2x plus, now what is the derivative of y squared with respect to y? 2y. Okay? Times dy dx. That's really handy that that's there, because that's what we're actually looking for. So 2y times dy dx equals 0. Now remember, our task here was to find the derivative, dy dx. So now we can say, therefore, rearranging this, 2y dy dx equals, take the 2x, or subtract 2x from both sides, equals negative 2x. You made it there. Therefore, dy dx equals negative 2x over 2y equals negative x over y. There is an expression for our derivative. Interesting here that the derivative is actually expressed in terms of both x and y. It's a bit like when we did it with the partial fraction, parametric equations. The derivative was in terms of the parameter, in terms of t or theta. Normally, dy dx, everything you've done in Maths B or in other maths topics, the derivative is always expressed in terms of x, but here it's in terms of x and y. Okay, so now we've got an expression for the derivative. Coming back to the original question, now we can find the equation of the tangent. So I'll rub this one out. And we want to know the equation of the tangent at this point, at 3, 4. So we could say, now, dy dx evaluated at 3, 4, the notation we can use there, is equal to, straight on from this, negative x, so negative 3 over the y value was 4. So the gradient on this curve at the point 3, 4, at this point here, is negative 3/4. Just a quick check in your head. Does that make sense? Yeah, it makes sense that it's negative anyway. And 3/4, it's close to 1. So it's nearly a 45-degree angle, which is probably about what it would be there. So, quick double check in your head, that's probably the correct answer. Therefore, y minus y1 equals mx minus x1 to find the equation of the tangent. Y minus y1, our point was 4, equals negative 3/4 x minus x1, our point was 3. Now it's just a matter of rearranging. Y minus 4 equals, actually before I do that, because this is going to be messy expanding it, I'm going to multiply right through by 4. So that'll give me 4y minus 16 equals, multiply this side by 4 and those 4's will cancel, so I'll get negative 3 brackets x minus 3. Got rid of all the messy fractions, so 4y minus 16 equals negative 3x plus 9. And then let's put it in standard form. 4y plus 3x equals, alright, 25. And this is equation of tangent. If the question asks for the equation of the normal, we would go through this same process up to here. The equation of the tangent, we would still get to there. But what would be our gradient of our normal if this is the gradient of the tangent?
1 minus.
Negative 1 over that. Okay? So basically in a easy way to do it, reciprocate that, so you get 4 over 3 and make it positive. Change the sign and do the reciprocal. I can do a couple of examples on that in a moment. Alright, what I'm going to do is one more question, but not through to its entirety. All I'm going to do is the derivative. So I'll do one more example here. One more example, and it will be just finding the derivative. Okay, find dy dx if x squared plus y squared minus 6x plus 8y minus 25 equals 0 at the point negative 2, 1. So this time I'm not going right through finding the whole equation of the tangent, etc., but just finding the derivative, because I want to make sure you can do this the implicit differentiation. Okay, Implicit differentiation, differentiate every term with respect to x. So here goes, the derivative of x squared plus the derivative of y squared minus the derivative of 6x plus the derivative of 8y minus the derivative of 25 equals the derivative of 0. So I've done d over dx, the derivative of every term with respect to x. It's a bit time consuming writing it out. Okay, if you need to just hold your writing for a moment, just maybe follow, because I won't run this out before you have a chance to do it. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x, 2y dy dx is what it's going to be. I'll put the working in here. It'll be the derivative with respect to y of y squared multiplied by dy dx. That's a little use of chain rule. The dy is basically cancelled and you're left with what we started with. Minus, we can do this straight off, the derivative of 6x with respect to x, just 6, plus here, chain rule again, we can differentiate 8y with respect to y, but we'll need to multiply by dy dx, chain rule again, minus derivative of 25, 0 equals 0. Simplifying that, 2x plus 2y dy dx. Oops. 2y times dy dx minus 6 plus, what will this one be? 8 times dy dx equals 0. Now it's a matter of rearranging this to get dy dx equals. It's a bit harder than that last example I did because you've got dy dx occurring in two places. What I'm going to do is get rid of everything from the left hand side that doesn't have a dy dx in it. So I'll leave this here. I will leave that one. And I'm going to take the 2x over, and I'm going to take the 6 over, and we're getting closer. Now dy dx still occurs in two places. What could we do here to get dy dx on its own? Dy dx, yeah, factorise. Dy dx is a common factor. 2y plus 8 equals negative 2x plus 6. Now this is multiply, remember? So to get dy dx on its own now, dy dx equals negative 2x plus 6 over 2y plus 8. There's an expression for the derivative of this, which is actually an ellipse. Therefore, dy dx evaluated at negative 2, 1 equals can we do that in our head? Oh, negative 2 times negative 2 plus 6 over y is 1, 2 times 1 plus 8, which is 4 plus 6 is 10 over 10 equals 1. So the gradient at this point of this curve, which is an ellipse, is equal to 1. So if you're finding the tangent or the normal, you could now use the gradient and do your y minus y1.